The idea that traveling to the past might someday be possible is no longer just science fiction. It's a tantalizing puzzle that challenges how we understand reality itself. Imagine bending time, looping back to moments long gone, or even changing history. Yet every step forward into this realm raises paradoxes that make the mind spin. Could we visit ancient civilizations, witness the birth of stars, or prevent historic disasters? Or might we get entangled in contradictions that threaten the very fabric of time? Stay with me, because unlocking this mystery could reshape everything we think we know about existence, hope, and the endless possibilities that lie just beyond our grasp. The concept of time in physics. In the realm of physics, time is far from being a simple, absolute ticking clock. Instead, it's woven into the fabric of space-time, a four-dimensional continuum where space and time intertwine in complex ways. Einstein's theory of relativity revolutionized our understanding by illustrating that time is relative, stretching and contracting depending on velocity and gravity. When objects move near the speed of light or are subjected to intense gravitational fields, time itself could behave differently than it does for a stationary observer. This relativity opens the door, at least theoretically, to the possibility of manipulating or even reversing the flow of time under certain extreme conditions. The concept of closed time-like curves, CTCs, in general relativity introduces a tantalizing idea: paths through space-time that loop back on themselves. These loops suggest that, in a highly curved universe, one could theoretically travel back in time along a path that doesn't violate the underlying mathematical structure of the equations. Solutions like the Gödel universe or traversable wormholes, hypothetical tunnels connecting distant points in space-time, are often cited in discussions about time travel. Wormholes, in particular, could act as shortcuts, potentially allowing an object or information to move from one point in time to another. However, translating these solutions from mathematics into physical reality is riddled with paradoxes and unresolved technical challenges. Entanglement in quantum physics adds another layer to the discussion, subtly hinting that information might be entangled across different points in time. Though this doesn't mean backward in time travel in the traditional sense, it compels scientists to reconsider how causality and information flow work at the fundamental level. If information can be correlated across time in a way that defies classical causality, then the limits of temporality might be more porous than once thought. Still, these phenomena challenge our notions of cause and effect, raising questions about free will, paradoxes, and the nature of reality itself. Despite the paradoxes and extreme complexities, the idea that traveling to the past might someday be possible fuels a hopeful sense of discovery. Each insight into the fabric of space-time suggests that the universe might contain loopholes or exotic conditions where time could bend or loop back on itself. While practical backward time travel remains a distant dream amid current scientific constraints, the ongoing pursuit of a unified theory that melds quantum mechanics and gravity keeps hope alive. It's a quest infused with wonder, challenging assumptions, pushing the boundaries of what we consider possible, and inviting us to imagine a universe where the past isn't fixed, but a terrain we might one day explore once again. Historical perspectives on time travel. The idea that traveling to the past might be within the realm of possibility has intrigued thinkers far before modern physics formalized the concept. Ancient stories and myths often hinted at time's fluidity, imagining portals or devices capable of transcending chronological boundaries. While these tales were symbolic or supernatural at their core, they planted seeds of curiosity that persisted through centuries, influencing early scientific inquiry. In the 19th century, as physics evolved with the development of concepts like the ether and electromagnetism, some scholars started contemplating whether the fabric of space-time could be manipulated to bend or fold in ways that might allow backward travel. From a more scientific vantage point, Einstein's theory of general relativity introduced the idea that space-time is flexible, capable of warping under the influence of mass and energy. This opened theoretical doors toward constructing worlds with closed time-like curves, which in principle could allow an object or even a person to loop back into their own past without contradiction. Such geometries, like those described by solutions such as the Gödel metric or the Tipler cylinder, remain speculative but suggest that the universe's structure might permit time travel under extreme conditions. These ideas, however, raise profound paradoxes, like the famous grandfather paradox, highlighting deep logical puzzles about causality and free will. Historical scientific debates have often revolved around whether such solutions could be physically realistic or will be destabilized by quantum effects. The consensus, at least historically, has been that the universe might forbid actual time travel to the past through some as yet undiscovered laws or principles. Nonetheless, theoretical models like wormholes, initially derived from Einstein-Rosen bridges, present tantalizing possibilities. If wormholes could exist and be stabilized through exotic states of matter, they might act as shortcuts across space-time, including into the past. Arguments abound over whether such constructs could ever be safely traversed or whether they inevitably lead to destructive feedback loops or paradoxes. Nevertheless, these perspectives from physics are not purely cold and mathematical. They evoke a sense of wonder at the universe's possible hidden dimensions. The ongoing debate about whether time travel to the past could ever be realized stirs philosophical questions about our understanding of reality, consciousness, and destiny. Despite the many hurdles, such ideas keep alive a hope that, someday, the mysteries of space-time might unlock a way for humans to peek behind the curtains of history and step into moments long gone. The beauty lies in the possibility, no matter how distant, that the past, with all its stories and secrets, might one day be accessible again. The nature of space-time and its properties. Space-time, as understood through Einstein's theory of general relativity, weaves space and time into a four-dimensional fabric that bends and twists in response to mass and energy. Unlike the classical view of an absolute, unchanging stage, space-time is dynamic, capable of warping profoundly around massive objects like black holes, causing phenomena such as gravitational lensing and time dilation. This interconnected nature means that events aren't just fixed in space and time, but are part of a flexible tapestry that can curve, stretch, or even potentially loop back on itself. The properties of this fabric are essential when theorizing about traveling into the past. If space-time can curve enough, if it forms closed loops called closed time-like curves, then traveling along such a path might lead one to an earlier point in history. This possibility hinges on the idea that the geometry of space-time itself isn't necessarily linear or unbreakable, but can contain loops that permit returning to an earlier moment. Some solutions to Einstein's equations, such as those involving rotating black holes, Kerr black holes, or hypothetical structures like traversable wormholes, seem to suggest that space-time could potentially be manipulated into these loops. However, these configurations come with mind-bending paradoxes and unresolved questions. For example, the famous grandfather paradox questions what happens if you travel back in time and alter events. Would that erase your own existence? From a physics standpoint, certain models imply that the universe might have mechanisms to prevent such paradoxes naturally, perhaps through quantum effects or cosmic censorship hypotheses. Still, the mathematical properties of space-time do allow for speculation that past travel might be more than just theoretical fancy. It could be rooted in the fundamental structure of reality itself. For now, understanding the fluid, highly curved, and sometimes paradoxical features of space-time keeps the door open to possibilities once thought impossible, fueling curiosity about the very fabric of the universe and its secrets. General relativity and wormholes. General relativity, Einstein's groundbreaking theory, reshaped the way we understand gravity, not as a force but as the curvature of space-time itself. This conceptual leap opened doors to fascinating possibilities that once seemed purely science fiction. Among them, the existence of wormholes, hypothetical tunnels in space-time, captured imaginations due to their potential to connect distant points across the universe, or perhaps even different moments in time. The mathematics of Einstein's field equations admit solutions that describe wormholes, suggesting they could, at least theoretically, exist within the fabric of our universe. These wormholes are not just simple bridges. They would require exotic matter with negative energy density to remain open. This exotic matter could, in theory, counteract the natural tendency of a wormhole to collapse under gravity. If stable wormholes could be created or stabilized, they might enable shortcuts through space-time that bypass the usual cosmic distances and durations. But when it comes to time travel, the idea becomes even more intriguing and paradoxical. If a wormhole connected two different times, say, the present to the past, then traveling through it could allow someone to arrive at an earlier point in history. However, this opens a Pandora's box of causality issues, like the famous grandfather paradox, where actions in the past could prevent your own existence. Physicists have explored various models, such as the Morse-Thorne wormhole, delving into what conditions would be necessary to make time travel possible without creating contradictions. These models show that, at least theoretically, if you could manipulate the space within a wormhole, you might one day solve the paradoxes through mechanisms like parallel timelines or quantum effects mitigating the contradictions. Still, the energy requirements are extraordinary and may well be beyond anything we can achieve with current or foreseeable technology. The mere possibility hinges on understanding, or even discovering, forms of matter and energy that defy our conventional physics. One of the most hopeful aspects lies in the idea that wormholes could serve as natural laboratories for understanding the universe's fundamental structure, especially at the intersection of general relativity and quantum mechanics. While nothing near completion exists for practical time travel, each breakthrough in gravitational physics brings the once unfathomable closer to the realm of possibilities. This tantalizing fit of physics and impossibilities keeps the spirit of scientific inquiry alive, suggesting that, within the fabric of space-time, there might still be secrets waiting to unravel, perhaps even the means to peek into the past. Theoretical existence of closed time-like curves. In the realm of theoretical physics, the concept of closed time-like curves, CTCs, offers a tantalizing glimpse into possibilities that challenge our understanding of causality and the flow of time. These loops in space-time allow an object or information to return to its own past, creating a path that, if followed, would eventually lead back to the origin point in time without violating the equations of relativity. The mathematics underlying CTCs emerges from solutions to Einstein's field equations, notably in specific space-time geometries, such as the Kerr black hole or the Gödel universe. These solutions suggest that, under certain conditions, nature might permit pathways through space-time where conventional cause and effect relationships could bend or even fold onto themselves. Fundamentally, the existence of CTCs hinges on the peculiar properties of space-time metrics that allow for closed loops in the time dimension. For example, in the case of a rotating black hole, also known as a Kerr black hole, the intense gravitational and rotational forces deform space-time in such a way that paths looping around the black hole might theoretically bring you back into the past. Likewise, the Gödel universe, constructed as a solution to Einstein's equations, is a universe woven with CTCs, illustrating that the universe's structure, if it were different, could inherently contain these peculiar time loops. These ideas stretch the imagination but are rooted in rigorous mathematical frameworks, making them credible topics within theoretical physics. Such possibilities immediately raise profound paradoxes and questions. If traveling back in time via CTC becomes feasible, what happens to free will or the fabric of history itself? The infamous grandfather paradox demonstrates how seemingly simple actions, like preventing your own existence, become complex logical puzzles within these constructs. Yet, some physicists argue that nature might have mechanisms to prevent such paradoxes, perhaps through the self-consistency principle, which states that any event occurring on a CTC must be self-consistent. In essence, the universe might impose constraints to avoid contradictions, allowing the existence of CTCs without resulting in logical chaos. This balance between possibility and paradox fuels ongoing debates about whether closed timeline curves are just mathematical curiosities or potential features of the universe's true structure. Exploring the theoretical existence of CTCs opens a window into both the limits of current physics and the imaginative realms of what might be possible. It sparks hope that the universe holds secrets enabling us to revisit moments in the past, possibly for scientific, philosophical, or even personal reasons. While no experimental evidence confirms the presence of CTCs, their mathematical plausibility invites us to reconsider the nature of time itself. The dream of traveling through such loops is no longer mere fantasy. It's a compelling aspect of modern theoretical inquiry, urging us to look beyond the confines of conventional reality and ponder what time could truly be if the laws of physics allow. Quantum mechanics and parallel universes. Quantum mechanics, with its curious principles and counterintuitive phenomena, opens a tantalizing window into the possibility of traveling through time by way of parallel universes. Unlike classical physics, which treats time as a fixed line, quantum mechanics suggests a landscape where multiple outcomes coexist in a vast, branching multiverse. This is best exemplified by the many worlds interpretation, which posits that every quantum event creates new, divergent universes. In this framework, every decision, measurement, or act of observation spawns an entirely new universe, leaving behind a web of interconnected but separate realities. This perspective implies that what we perceive as the past might be just one thread among infinitely many. If parallel universes coexist, then changing something in one universe could, in theory, reroute the timeline or even facilitate movement between these realities. Unlike the time travel often depicted in science fiction, where a person zips back and forth within a single timeline, these theories suggest that one could access alternate paths through pathways that bridge different branches. These pathways bypass the paradoxes associated with traditional backward time travel. For example, the infamous grandfather paradox, where one could potentially prevent their own existence by altering the past, might not hold if you can simply move into an alternate universe where those changes have already occurred without affecting your original reality. Furthermore, certain interpretations of quantum mechanics hint at mechanisms that could allow for the encoding and decoding of information across these universes. Quantum entanglement, which links particles instantaneously over vast distances, hints at a deeper interconnectedness that could, in theory, extend to larger scales, potentially enabling a form of communication across parallel worlds. While we are far from practical methods to harness such phenomena for travel or communication, the theoretical groundwork sparks hope that these mysteries might someday be harnessed in ways we can't yet fully grasp. The idea that different universes could serve as different destinations for a sort of quantum shockwave or portal remains speculative but tantalizing. In essence, the notion that traveling to the past could be realized through the lens of quantum mechanics and parallel universes transforms our understanding of causality and history. It hints at a future where time travel isn't about bending or breaking the rules of a rigid timeline, but about navigating a complex, interconnected web of realities. This perspective fuels a sense of wonder, highlighting that what once seemed impossible, altering history or revisiting bygone eras, may not only be within the realm of possibility, but could also redefine how we see existence itself. The universe, with its infinite branching, might hold mechanisms we have yet to discover, making the idea of traveling through time not just a science fiction fantasy, but a genuine scientific frontier waiting to be explored. The role of exotic matter and energy conditions. The concept of traveling to the past often evokes images of science fiction, yet physicists have explored the theoretical underpinnings that might make such journeys possible. At the core of many of these ideas lies the peculiar requirement of exotic matter, substances with properties that defy ordinary physics. Unlike familiar matter, which obeys the energy conditions dictated by general relativity. Exotic matter would possess negative energy density or negative pressure, qualities necessary to stabilize certain hypothetical structures like wormholes. These structures, if stabilized, could serve as shortcuts through space-time, allowing travelers to effectively move backward in time. In classical general relativity, energy conditions ensure the stability and causality of spacetime. However, to keep a traversable wormhole open, the average null energy condition must be violated. This is where exotic matter comes into play. Its negative energy density counteracts gravitational collapse, preventing the wormhole from pinching off. Quantum effects, such as the Casimir effect, offer a tantalizing glimpse into negative energy phenomena. Pairing of virtual particles creates regions with negative energy density somewhere between conducting plates. While the Casimir effect has been experimentally confirmed, the amounts of negative energy necessary for a wormhole stability are many orders of magnitude beyond current technological reach. Energy conditions are thus central to the theoretical feasibility of time travel. Physicists debate whether exotic matter can genuinely exist or whether these are mere mathematical artifacts. Some theories propose that quantum fields could generate enough negative energy locally to stabilize a wormhole, but these are speculative. The paradoxes that arise from temporal loops, like the grandfather paradox, highlight the tension between general relativity and the laws of quantum mechanics. Still, the hope persists that new physics, perhaps arising from a unified theory of quantum gravity, might allow for exotic matter's existence without destroying the universe's causal structure. In essence, exotic matter serves as a bridge between the seemingly impossible and the potentially feasible. It embodies the idea that our universe might host phenomena that challenge our everyday notions of energy and matter. The pursuit of understanding these energy conditions is driven not only by the quest for practical time travel, but also by a deeper curiosity about the fundamental fabric of reality. The notion that negative energies could manipulate space-time suggests a universe rich with possibilities, where paradoxes might be resolved or rendered irrelevant by yet unknown laws. Such ideas ignite hope that, someday, what now seems like pure science fiction could become a profound chapter in our understanding of the cosmos. Energy requirements for creating time loops. The concept of bending space and time to traverse backwards hinges on delving into the realm of energy, specifically how much it would take to initiate and sustain a time loop. At the heart of many theoretical models, such as those involving wormholes or closed time-like curves, lies the need to manipulate space-time itself. To create and maintain these distortions, an immense amount of energy must be concentrated in extraordinarily precise ways, often surpassing anything conceivable with current technology. For instance, some hypotheses suggest that reversing the flow of time in a localized region might require energy densities comparable to those present during the earliest moments after the Big Bang, where matter and energy were compressed into exotic states. The key paradox here is balancing the enormous energy costs with the physical constraints of the universe. Negative energy, or exotic matter, often appears as a hypothetical ingredient to stabilize wormholes or other time travel mechanisms. Such exotic matter would possess properties that violate the usual energy conditions, implying it might require an unthinkable amount of energy, perhaps on the order of entire planetary masses or greater, just to sustain a tiny loop in time. This creates a paradox. If extracting or generating that amount of energy were possible, it would likely require fundamentally new physics, perhaps involving unknown quantum fields or undiscovered particles that could tap into vacuum fluctuations on an enormous scale. However, some theoretical approaches entertain the idea of harnessing quantum phenomena or high-energy cosmic events, like black hole evaporation or cosmic strings, as potential sources for the vast energy needed to produce a time loop. These approaches, although speculative, raise interesting questions about whether the energy could be harvested from the universe itself. For example, if a sufficiently advanced civilization could manipulate the Hawking radiation emitted by a microscopic black hole, the energy costs might become more manageable, at least theoretically. Yet, this would still mean working with energies on a cosmic scale, where even tiny miscalculations could cause catastrophic feedback loops, destroying the very fabric of space-time you're trying to bend. All of this underscores the paradox at the core of temporal engineering. To travel in time, the amount of energy required could be so vast that it encourages reconsidering the principle of feasibility altogether. But the sheer scale of energy involved does not extinguish hope completely. It fuels the curiosity that pushes scientists to think beyond our current understanding, hinting that perhaps in some distant future, unknown methods of energy manipulation, maybe quantum teleportation of energy or vacuum energy extraction, might make traveling through time a reality. For now, the challenge remains a titanic puzzle, blending impossibility and hope into a tantalizing frontier of physics. Stability and causality concerns in time travel. The notion of traveling back in time invites a fascinating web of theoretical and practical challenges, especially when it comes to maintaining the fabric of causality. If a person were to journey into the past, even the slightest alteration could ripple through history in unpredictable ways. This brings into question the very stability of timelines. Could the universe inherently resist such disturbances, preserving a consistent history? Or do small changes snowball into paradoxes that threaten to unravel the entire causal structure? These questions are at the heart of many theoretical debates. Physicists have proposed that certain conditions or mechanisms, like the concept of a self-consistent universe, might prevent paradoxes, ensuring timeline stability. This idea suggests that the universe might be fine-tuned to prevent any influence that would cause a contradiction, such as the famous grandfather paradox, where going back and preventing your own existence would create a logical inconsistency. Causality, the relationship of cause and effect, is perhaps the most fragile aspect of this puzzle. If time travel were possible and causality could be disrupted, it raises the specter of paradoxes that could undermine the very notion of history or free will. For example, if a traveler intervened in a pivotal event and altered its outcome, would subsequent events change accordingly, or would the timeline simply resist? Some theoretical models suggest that, in certain space-time geometries, such as those featuring closed time-like curves, causality might be fundamentally broken or at least bent into strange loops. This creates a scenario where cause and effect are no longer straightforward, giving rise to what's called a causal loop, where events can influence themselves. While captivating, this concept raises profound questions about determinism and the nature of reality. A hopeful perspective lies in some interpretations of quantum mechanics, which entertain the possibility that multiple timelines or parallel universes could serve as a kind of safety valve for causality. If every change you make splits the universe into a new branch, then paradoxes become less problematic, though time travel would then be about moving between these branches rather than altering a single, fixed timeline. The idea that the universe might be layered with countless alternate histories shields causality from collapse, but also complicates our sense of identity and linear progression of events. Still, this keeps the door open to distant future theories where consistency could be maintained without sacrificing the fundamental fabric of cause and effect. It infuses hope that, even amid such profound intricacies, the universe might have an inherently resilient structure designed to accommodate the possibilities of time travel without descending into chaos or paradox. Potential paradoxes and resolution theories. When contemplating the possibility of traveling back in time, one of the most captivating and challenging aspects to confront is the array of paradoxes that surface from altering past events. The most famous among them is perhaps the grandfather paradox, in which a time traveler could inadvertently prevent their own existence by interfering with ancestors. Imagine preventing your grandparents from meeting, and suddenly, your own existence becomes impossible. It whispers of a universe where cause and effect are entwined in a delicate, perhaps fragile, tapestry. Yet, these paradoxes aren't just philosophical curiosities. They serve as crucial touchpoints that shape scientific debate and theoretical exploration. Resolving these paradoxes has led to fascinating theoretical frameworks that endeavor to reconcile time travel with logical consistency. The many-worlds interpretation, borrowed from quantum mechanics, suggests that every time a decision or change occurs, the universe splits into separate branches. In this view, crossing into the past creates an alternate timeline where actions influence only that branch, leaving the original timeline untouched. This notion alleviates the grandfather paradox because the traveler's interference results in a new, independent universe rather than altering their own history. However, it raises questions about the nature of reality. Are these separate worlds accessible, or are they forever isolated? Still, it offers a hopeful resolution where paradoxes are not outright forbidden, but merely manifest in different, parallel spheres. Another approach is the self-consistency principle, championed chiefly by physicist Igor Novikov, which posits that any actions taken while traveling to the past must be inherently self-consistent. In essence, the universe's fabric is arranged so that paradoxical situations cannot arise, preventing, for example, the accidental killing of one's own ancestors if it results in a contradiction. This perspective suggests that if a time traveler attempts to change the past, unforeseen circumstances or even physical laws would conspire in ways that preserve consistency. Like a cosmic safety net, it ensures the paradoxes remain theoretically impossible without denying the very possibility of altering past events altogether. Both theories stir hope that, should time travel ever be possible, it wouldn't necessarily unravel the logical fabric of reality, but would unfold within it in a way that respects its integrity. While these conceptual resolutions remain speculative and face formidable scientific and philosophical challenges, they embody the boundless human desire to understand, explore, and even reconcile the mysteries of time itself. The paradoxes serve not just as obstacles, but as catalysts, kind of like puzzles that push the boundaries of modern physics and thought experiments. Though practical time travel remains far from realization, reflecting on these theories sparks optimism about what the future might hold, illuminating the profound interconnectedness and resilience of the universe's structure, waiting to be unraveled. Technological challenges and feasibility. The idea of traveling to the past hinges on overcoming formidable technological barriers, many of which seem rooted in fundamental physics itself. Currently, our understanding of space-time, particularly through Einstein's theories of relativity, suggests that manipulating time in a controlled, purposeful manner would require conditions and materials far beyond what modern science can produce. For example, the concept of a wormhole, a hypothetical tunnel connecting distant points in space-time, is often cited as a potential route for time travel. However, creating or stabilizing such a construct would necessitate exotic matter with negative energy density, something that remains purely theoretical. The energy requirements alone could be astronomical, possibly exceeding the total energy output of entire stars, and no known technology today can access or generate such levels. On a more practical level, even if we bypass the exotic materials dilemma, issues of precision and stability arise. The immense gravitational forces involved in warped space-time could distort any machinery or technology intended for time travel. Such forces could rip apart or destabilize a device designed to manipulate time, leading to unpredictable consequences. It's akin to trying to build a bridge across a turbulent river, except that here, the river's currents are the fabric of the universe itself, constantly shifting and bending. The more our understanding advances, the more we see that each step toward feasible time travel demands breakthroughs, not just in physics, but also in materials science, energy storage, and quantum computing. Furthermore, the paradoxes attached to traveling to the past introduce complexities that are as much philosophical as they are technological. Technologies capable of sending information or matter back in time would require precise control over temporal dimensions, which, in turn, implies an incredibly detailed understanding of the universe's structure at its most fundamental level. Current models of quantum gravity suggest that space-time could be discrete rather than continuous, adding a layer of unpredictability. These uncertainties make reliable, safe time travel seem like an insurmountable problem with the technology of today. Yet, the sheer audacity of these ideas fuels ongoing research and imagination, hinting that perhaps in the distant future, some new physics might emerge to bridge the gap. Amidst all these challenges, there's a surprising note of optimism. Science often advances in leaps when theoretical boundaries are pushed, and history is littered with ideas once deemed impossible that later became reality. The notion that we might someday develop the means to manipulate space-time hinges on breakthroughs that could redefine the very fabric of technological possibility. Our current limitations are merely the starting points, not the endpoints. When considering the future of time travel, it's not just about solving countless engineering and physical puzzles, but also about reframing what we believe is fundamentally possible. The road is steep, but if history teaches us anything, it's that the most ambitious questions often lead to the most profound discoveries. Implications for history and ethics. The possibility of traveling back in time opens a Pandora's box of philosophical and moral questions that challenge our current understanding of reality and morality. If it becomes feasible, whether through wormholes, quantum mechanisms, or another yet undiscovered method, then the fabric of history itself might not be as fixed as we once believed. Every action taken by someone in the past could ripple through the timeline, creating alternate histories or paradoxes that are difficult to reconcile. For example, the famous grandfather paradox illustrates what happens if a traveler were to unintentionally prevent their grandparents from meeting, potentially erasing the traveler's existence altogether. Yet, without such destruction, it raises serious questions about responsibility. Would a time traveler have moral obligations to avoid altering events? And if they did, would that restrict their freedom to explore? From an ethical perspective, this scenario introduces a tension between curiosity and moral restraint. On one hand, the ability to observe or even influence past events could be immensely enriching, offering insights into human nature, cultural evolution, and even solving historical mysteries. On the other hand, it risks creating a form of moral hubris, where those with access to time travel might feel entitled to correct historical wrongs or impose their values on the past. For instance, intervening to save individuals from tragedy could seem compassionate, but might also produce unforeseen consequences that create larger ethical dilemmas. Would moral mercy override the need to preserve the integrity of history? Or should the principle of non-interference be universal, akin to an ethical boundary designed to protect the natural course of events? Furthermore, the implications extend into questions of justice and accountability. If actions in the past can be altered, what does that mean for we who are living in the present? Would future societies develop a sense of moral relativism, where the ethical weight of actions depends heavily on when and why they're performed? Might there emerge a new moral hierarchy based on the timeline's stability? There's also the danger of manipulation. Individuals or regimes could exploit time travel to rewrite history for personal gain or political power, raising concerns about sovereignty and control over collective memory. Yet, amid these paradoxes, there's an undeniable sense of hope. Perhaps our understanding of ethics could evolve to incorporate these new dimensions, turning dilemmas into pathways for greater empathy and wisdom across the ages. The very notion invites us to rethink what it means to act morally when the boundaries of time itself become fluid. Current experimental and observational limits. Minds exploring the realm of time travel confront a landscape riddled with formidable experimental and observational hurdles. Despite the allure of bending temporal boundaries, our current scientific tools and methodologies fall woefully short of detecting or manipulating temporal shifts in any definitive way. For instance, the most promising avenue, studying the effects of relativistic phenomena in particle accelerators or celestial observations, has yet to reveal any signs of actual backward time travel. When particles reach near-light speeds in accelerators like the Large Hadron Collider, they experience time dilation. But this is strictly unidirectional and strictly obeys the forward flow of time. No evidence suggests that, even under extreme relativistic circumstances, the fabric of space-time behaves in ways compatible with reversing its direction. Observational limits are equally tight. The universe itself is age-dated through cosmic microwave background measurements and large-scale structure surveys, which effectively define a chronological boundary that we cannot algorithmically bypass. We see the universe's history imprinted in the light reaching us, but no anomalies indicate past versions of objects or signals from a different time. Even efforts to detect closed time-like curves, theoretical pathways in space-time that could permit time loops, have not yielded empirical clues. While some models suggest black holes or wormholes might host such phenomena, the reality remains that no experimental evidence supports their stable existence or traversability. The energies and space-time manipulations necessary to probe these exotic objects currently exceed our technological capabilities by multiple orders of magnitude. Furthermore, the observational tools at our disposal are inherently limited to signals encoded within the speed of light. We can observe distant stars and galaxies, but our ability to scrutinize their historical states depends on the time it takes for their light to arrive. Decades, centuries, or even millennia, creating a built-in delay. This window constrains our capacity to verify any hypothetical mechanisms of traversing temporal boundaries. Advances like gravitational wave detectors have opened new avenues to sense cosmic events in real time, but they do not bring us closer to witnessing or creating temporal loops. Instead, they reinforce that our universe adheres strongly to causality and time's arrow at large scales. All these limitations highlight an ongoing paradox. Despite the theoretical plausibility of traveling into the past, suggested by the mathematics of Einstein's relativity and certain quantum models, the empirical universe steadfastly resists such excursions. Yet the absence of evidence does little to diminish the vivid hope that future technology, perhaps rooted in a deeper understanding of quantum gravity or as yet undiscovered principles, might one day overcome these barriers. For now, our quest remains tethered to the observable horizon, a reminder that the universe's most profound mysteries often linger just beyond the reach of experiment, fueling both scientific curiosity and an enduring sense of wonder. Future directions and research opportunities. The pursuit to understand and perhaps harness the possibility of traveling to the past hinges on unraveling some of the most perplexing puzzles in physics and cosmology. Researchers are increasingly exploring the implications of wormholes, hypothetical tunnels in space-time that could, in theory, connect distant points across the universe, or even different moments in time. Intriguingly, some solutions to Einstein's field equation suggest that if such structures exist and are stabilized, they might enable temporal loops. The challenge lies in maintaining the stability of these wormholes, preventing them from collapsing or creating paradoxes, or finding natural conditions under which they might form without causing catastrophic effects. Advances in quantum mechanics offer promising avenues for future research. Quantum entanglement, despite its description as spooky action at a distance, raises questions about whether information could be transferred or even transmitted through time by exploiting quantum states. Though no current evidence supports sending information back in time, the theoretical groundwork might one day allow quantum fields or particles to interact with space-time in ways that challenge classical notions of causality. For instance, researchers are investigating whether quantum superpositions could create self-consistent loops, sidestepping traditional paradoxes, such as the famous grandfather paradox, by allowing only certain outcomes to be realized. These studies open tantalizing possibilities for controlled, paradox-free time loops, but they also demand a deeper understanding of the quantum gravitational interface. The invitation to think beyond conventional models encourages a multidisciplinary approach. Cross-pollination between string theory, loop quantum gravity, and holographic principles could unlock new pathways for manipulating space-time geometry. For example, some theories posit that space-time itself may be emergent from more fundamental quantum information processes. If this is true, then future research could explore how to manipulate that information structure to create temporary pasts, essentially constructing a controlled, causal reverse in the fabric of reality. Experimental efforts, though still nascent, might involve high-energy particle collisions or sophisticated simulations of space-time conditions where effects akin to negative energy densities, crucial for stabilizing wormholes, can be observed indirectly. Looking ahead, investigations into the nature of time itself, whether it is truly a linear progression or something more fluid, are crucial. Philosophical and scientific debates about the block universe concept challenge our understanding of past, present, and future. If time is indeed a four-dimensional manifold, then traveling to the past might not be about movement through time, but navigating within its structure. This perspective could redefine how future generations approach experimental physics, inspiring novel technologies that manipulate the space-time fabric in ways currently deemed speculative. Still, each discovery fuels both optimism and caution, as the paradoxes inherent in temporal travel demand innovative resolutions that could reshape science and philosophy in fundamental ways. The ongoing quest is a vibrant dance between bold curiosity and rigorous testing, where the boundaries of what is possible continue to expand with every breakthrough. The concept that traveling to the past might be theoretically plausible has long fascinated scientists and thinkers alike. According to Einstein's theory of general relativity, the fabric of space-time can be warped or curved by mass and energy, creating possibilities beyond classical understanding. This idea opens the door to the notion that certain geometries, such as wormholes or closed time-like curves, could serve as portals for temporal navigation. Wormholes, often depicted as tunnels connecting distant points in space-time, could potentially be used to traverse back in time if they exist and can be stabilized. While no empirical evidence yet confirms their existence, the mathematics underlying general relativity suggest such structures are not physically impossible, at least in principle. Paradoxes emerge naturally when contemplating the notion of traveling to the past. The grandfather paradox, where a time traveler could theoretically prevent their own existence, poses a fundamental challenge to causality. But some physicists propose that the universe's structure may inherently prevent such paradoxes through what are called self-consistency principles, where only event sequences that do not lead to contradictions can occur. This concept hints at a universe that is, in a sense, self-correcting. Others explore the idea of parallel or branching universes, where alternate timelines provide a workaround. Traveling back in time would simply create a new universe, rather than changing the original one. This multiverse perspective sidesteps paradoxes, but raises profound questions about the nature of reality and the interconnectedness of timelines. Technological pathways that could theoretically facilitate backward time travel often hinge on manipulating space-time geometries or harnessing quantum phenomena. For instance, some experimental models involve the use of quantum entanglement and superposition to simulate time travel or exchange information across time-like boundaries without violating causality in observable ways. While these experiments are far from actual time machines, they push the boundaries of what our current understanding permits and inspire ongoing research. Advances in quantum computing, gravitational wave detection, and space-time engineering might one day reveal methods to bypass current limitations, transforming whispers of science fiction into scientific potential. Despite its speculative nature, the possibility that time travel might one day be achievable fuels hope and curiosity. The theoretical frameworks demonstrate that, under specific conditions, moving through time could be consistent with the laws of physics. What's more compelling is that each discovery sheds light on the universe's underpinnings, its structure, dimensions, and the fundamental rules that govern existence. The future of this pursuit hinges on unraveling the deeper truths of space-time, quantum mechanics, and gravitation. If those elusive pieces fall into place, traveling back to the past might transition from a mind-bending paradox to an extraordinary reality, an achievement that transforms our understanding of reality itself. As we've explored, the idea of traveling to the past isn't just a whimsical dream. It's a tantalizing possibility grounded in the mysteries of physics and the paradoxes that challenge our understanding of time. From Einstein's theory of relativity to the intriguing concept of closed time-like curves, the universe seems to hold secrets that could, in theory, allow us to revisit moments long gone. Yet, the paradoxes like the grandfather conundrum remind us that time travel isn't just about bending space. It's about confronting the very fabric of reality and causality. It's this delicate dance between scientific possibility and the wonder of what could be that makes the pursuit so captivating. Maybe one day, we'll unlock the secrets that make traveling to the past feasible. Or perhaps we'll find that the universe guards its timelines fiercely. Either way, the journey of discovery enhances our understanding not just of time, but of ourselves and the universe we inhabit. So, whether history remains an unchangeable anchor or becomes a realm we can explore, the beauty lies in imagining what's possible. Keep pondering, stay curious, and don't forget, this is just the beginning of the questions. We'll be exploring more fascinating ideas and breakthroughs in future videos, unraveling the mysteries of our universe together. Until then, keep dreaming of what might be, and who knows, perhaps one day, the past might just open its doors to us.